Welcome to day 20 of the 2024 Advent of Code. For today's problem, we have another grid where we have a start and end position on a racetrack. The map consists of track, which is represented as dot, including the start and end, and the walls, which are represented by pound signs. I'm sure this format is very familiar. We've seen this many times this year. There's only a single path from the start to the end, and all the programs go at the same speed of one move per picosecond. And so we introduced a new rule to the races to make things a bit more interesting. You can cheat once per race, which allows you to disable collision for up to 2 picoseconds, and this allows you to pass through walls as if they were regular tracks. And when your cheat ends, the program has to be on the normal track or you will segfault and get disqualified. So for example, the completion can be done in 72 picoseconds by performing a skip here, which saves 12 picoseconds over the normal 84 picosecond route. Here we can skip past this bend by jumping through this wall. We can also save 20 picoseconds by skipping this B-shaped segment by jumping over this wall. We can save 38 picoseconds by skipping over this entire right half by jumping over this wall. And finally, the optimal strategy is to just skip from this directly to the end, saving 64 picoseconds. Each cheat is uniquely identified by the start and end position. So for example, if we had a situation like this, where we decided to cheat like this, then this route here and this route here would be considered the same. So the exact path does not matter, it's just where we start our cheat and where we end up that matters. So in the example, this is the number of cheats that saves each amount of time. We aren't sure what the conditions of the racetrack will be like, so we want to give ourselves as many options as possible. And so we'll need a list of all cheats that will save at least 100 picoseconds, and we want to know how many there are. So when I first solved this problem, I didn't read the problem statement clearly enough. Specifically, I missed the part about there only being one path, and so I used a standard breadth first fill. Now you could still do this, and when you're under time pressure, it's honestly probably faster than trying to think of a way to do it better. Let me just show you how I originally did this and how it can be done a bit better in hindsight. So first I'm going to grab the grid. And then we're going to search for the start position. And then if we don't break out of the loop, it means we didn't find anything. So we'll continue the road loop. And if we did break, then we skip the else block and break. This is a common pattern to extend the break. Basically, it means if this loop breaks, we can attach an else continue break to also cause the outer loop to break, which is essentially the same as being able to break the outer loop directly. I have a short on YouTube about this construction if you are interested in learning a bit more about it. And then using standard breadth first fill method, we would do from collections import deck to get our queue. Now, unlike usually where we just keep track of the distance to the current position so that we can find the distance to the end state, we will this time use a grid to represent the distance to every point. And the reason we're doing that is basically if we have a bunch of positions where we know the distance to every single one in between, 3, 4, 5, 6, 7, 8, then when we do our search eventually, we can look at each position, search for all of the positions we could cheat to, and then see if there are any that where the total difference between the regular track distance is greater than or equal to 100. So we will keep track of this in a grid where initially the distance to each point is, let's just say -1. And of course, the distance from the starting point to itself is equal to 0. And then we'll maintain a queue of all of the positions that we are tracking. Like in standard breadth first search, this essentially is a list of open positions, which are positions that we know we can reach, but have not yet explored the neighbors of. So now, so long as we still have open nodes to explore, we can take a look at the first one. So current row, current column equals q.popleft. And then we can look at all of its neighbors for an neighbor row, neighbor column in all of the cardinal direction neighbors. Like so. And then we can check first that they are within the grid and second that they are not a wall. So if nr is less than 0 or nc is less than 0 or nr is outside of the row bounds or nc is outside of the column bounds, then we skip it. And if the cell at that position is a wall, then we skip it. Additionally, distances will be a non-1 number for everything that we can reach. So if it's already not -1, that means we've already reached it before. And because we're doing breadth first search, meaning we're searching outwards and looking at the closest nodes first, essentially we are, if we imagine on a grid where there is more than one path, if we start here, we'd go to all of these 4 positions first, and then we go to these positions next. That means that if we ever come across a point again, that means that path must be inferior to the original path. So if we've already seen a node once, we don't need to look at it again. So if the distance to nrnc is already not -1, that means that we've already found a route to it and can skip over it. Now all that remains to do is update the distances. So the distance to get to nrnc is equal to the distance to where we currently are, plus the 1 move to get there. And then we also add it to the queue because it is now an open node that we know we can reach, but whose neighbors we have not yet explored. At the end, we will have a grid of distances. And if we run this on the test data, we can see that this is approximately what we get. So this all makes sense. This is the starting position, and all of the pound signs are -1s. It takes us 1 move to get here, 2 moves to get here. And if we search for the end here surrounded by -1s, we can see that, as stated in the problem, it takes 84 moves to get there if we don't use any cheats. Now this technically is not needed. We do not need to do a breadth first search. We do not ever have more than 1 open position because, like the problem states, there is only 1 path. And so we can shorten this code a bit. Now, like I said earlier, when you're doing this under time pressure, it probably makes more sense to just implement the method that you're confident and comfortable with. But let's try to do this another way. We're going to track this the same way, and then we're basically just going to update RC on the fly. So we can do a while grid RC is not equal to E, meaning we have not yet found the end. Then we can look through all of its neighbors. So we need to keep track of the neighbor that we're at. So for nrnc in all of its neighbors, r+1c, r-1c, rc+1, and rc-1. If the grid at that position, first of all, if that position is out of bounds, then we skip it. And if that position is equal to a pound sign, we also skip it. Otherwise, if it's in bounds and not a pound sign, that means it is a track block, and so we can update R and C to NR and NC, and we can also update the distances. So before we do that, we have a couple of other considerations we need to add. First of all, this does not circumvent backtracking because we could just go back and forth between 2 dots forever. So each time we leave a position, we're going to mark it as a pound sign. So we're going to do grid nrnc equals pound sign. And by setting the block to a wall when we leave it, it prevents us from returning to it. Or actually, this is unnecessary because we could also just say if dists nrnc is not equal to -1, that means we've already visited it before. And then we also need to update the distances value. So the distance to nrnc is equal to 1 more than the distance to our current position. And then we update our current position to the only possible track cell that we have found. Eventually this loop will complete because R and C will point to the coordinates of the end position, at which point we will terminate. And so this will give us the exact same thing as part 1, but a bit simpler, a bit more straightforward, because we technically do not need to do a breadth first fill here. We just need to look for the sole possibility that exists. So now what do we do with this? Like I mentioned earlier, we're going to look at each cell and look at all of the possible positions we could cheat to, and then we will find how many of them are going to save us more than 100 picoseconds. Now note that because it takes us 2 picoseconds to get from here to our cheat position, that means that the difference between them needs to be at least 102 picoseconds. If it were only 100 picoseconds, for example, then going this way would take 100 picoseconds and going this way would take 2, which means we've actually only saved 98 picoseconds. So we will maintain a count, and then we'll do another double loop for R in range rows and for C in range columns. First of all, we need to make sure that this is not a wall, so if dists RC is equal to -1, continue, or equivalently you could do if grid RC is a £, continue. And then we'll look at all of the positions we could cheat to. To avoid double counting, there are 2 ways we could do this. We could either start at each position and look at all 8 positions we could cheat to, and only count it if this one is greater than the neighbor. Alternatively, what we can do is, starting from each point, we only look at half of the possible cheat positions and allow them to be in either order. That way, each pair will only either be represented by its top left corner, its left corner, its bottom left corner, or its top corner. This connection here would only be searched when we look at this node and look down, because we will not look up. During the contest, I chose this method because it saves us a bit of time typing out the cheatable positions. It's up to you which one makes more sense. I'll show both quickly. So we can do for NR and C in R plus 2C, which is down, R plus 1C plus 1, which is down and then to the right, RC plus 2, which is directly to the right, and R minus 1C plus 1, which is up and to the right. We have 2 conditions again. First of all, it needs to be within bounds. And it needs to not be a wall. And then we'll look at if it is close enough. So if the absolute difference between the distance to R and RC and the distance to NRNC is at least equal to 102, that means that jumping from this position to this position in 2 picoseconds will save us at least 100 picoseconds. So we can do count plus equals 1. Right, this needs to be NRNC. That would work for a solution for part 1. Alternatively, if we want to look at all of the 8 directions and not allow arbitrary directions, then we can remove the absolute value here and add in the remaining values. So we'd also need to look up and to the left, directly to the left, and down and to the left. So this will also give us an answer for part 1. I personally am a fan of the method of only looking at half the cases and just allowing them to be in either order, but it is entirely up to you which one you think makes more sense. So that gives us our answer for part 1. Before we move on to part 2, I'd like to take a moment to announce a giveaway and introduce my sponsor, CodeCrafters. Many people ask me how I learned to code, and I've always learned best by actually going in hands-on with a project or problem rather than reading documentation or tutorials. That's why I love CodeCrafters, a platform that lets you build real-world software to both develop your problem-solving skills and train you in a specific language of your choosing. CodeCrafters lets you choose something to build, such as a BitTorrent or Git clone, and a language from a growing selection of over 20 languages and counting. You simply clone a repository from them, write your code to build your project with their intuitive step-by-step process, and push to get immediate feedback. Whether you're a beginner or already experienced in a language, CodeCrafters is a great way to start coding, pick up a new language, or master your language with its selection of projects. Doing a project teaches you more than just coding, as you can learn about protocols and existing software. If you sign up for free via my link in the description, you'll get 40% off if you choose to upgrade, which unlocks more content, gives you priority on test runs, grants access to perks which can save you money on all sorts of other platforms, and more. Plus, if you sign up within this December, you'll get access to all of the problems for free for 1 week. If you work at a company with learning and development benefits, be sure to check if Codecrafters would qualify so you don't even need to pay for it yourself. Codecrafters is also giving away several subscriptions, and you can enter to win one right now. Up for grabs are a lifetime membership for 1 lucky participant, 2 one-year plans, and 3 3-month plans for a total of 6 chances to try out Codecrafters and master your language or learn that language you've been meaning to try out. To enter, just comment your GitHub handle and one thing you love about Advent of Code on this video, and sign up for an account via my link. You don't need to upgrade your account to enter, and winners will be drawn with fair odds for everyone. Also make sure you're subscribed so you don't miss other videos and opportunities like this. Thank you for your support, and let's get on with the rest of the video. For part 2, it turns out that the 2 picosecond cheating rule was already deprecated, and the latest version actually allows a single cheat that lasts up to 20 picoseconds instead. So a lot more cheats are possible now. And so, for example, we can save 76 picoseconds by taking a 6 picosecond cheat from here to here. Note that the following cheat from here to here, going right and then down instead of down and then right, is considered the same cheat. Although the path is different, the starting and ending position of the cheat is the same as above, which is how we uniquely identify cheats. Cheats also don't need to use all 20 picoseconds. They can last up to and including 20 picoseconds, but you can still only end them when the program is on a normal track. And so we still need to figure out how many cheats will let us save at least 100 picoseconds. So previously we looked at all possible outcomes, which really was just jumping through a wall going down, jumping through that wall going right, or through another wall going right like so, jumping over the right wall, or jumping over a wall and then going up like so. So these were the 4 possibilities at radius equal to 2. What we can now do is look at the radius for all points between 2 and 20 inclusively, and then just look at all of the points in the diamonds surrounding those. So this is the way I solved it, and this is slightly inefficient. I'm still trying to work on a more efficient solution that doesn't take several seconds to run. I will probably do a recap stream this year as well to revisit a couple of the problems with some better approaches in hindsight. And so this is definitely one that I would be interested in looking at again. If you have any ideas, please feel free to let me know in the comments below. So instead of looking through just the points at distance 2, we're going to look at the points from distances from 2 up to and including 20. So for a radius in range from 2 up to 20 inclusively, we will look at all of the points along that diamond shape. And so the way we're going to do that is we're going to track a row distance counter and a column distance counter, or rather the column distance counter will be computed. The row difference could be anywhere from 0 to the radius inclusively, and then the column difference is just the radius minus the row difference. So we can do that like so for distance in row in range from 0 up to the radius inclusively. The difference in column is the radius minus the difference in row. And then the points that are possible given that row and column displacement are positive, 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 negative, negative, positive, and negative, negative. Now note that if dr or dc is equal to 0, we will have duplicates of the corner cases. We can exclude that by just making the following a set. So we'll loop nr and c in a set of the possible options. Positive, 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 negative, negative, positive, and negative, negative. The rest of the logic follows nearly identically. We need to make sure this is not out of bounds, and we need to make sure that we're not ending in a wall. And instead of 102 here, it needs to be 100 plus the radius, because the point was basically that using the cheat, it takes us 2 picoseconds in part 1 to get from RC to NRNC. Now it takes us radius picoseconds. So in order to save 100 or more picoseconds, the original distance has to be greater than or equal to 100 more than how long it is going to take us now. Finally, another thing we need to know is that we need to drop the absolute value here because we are now looking at all possible connections from each point, which means that we're no longer getting the benefit of eliminating double counting via only looking at half of the options. This, in my opinion, was easier when we had when we had to hard code each of the values, but this makes more sense now that we are looping through this in this method. So we're just going to drop the absolute value here. And this code, like I said, does take a significant amount of time to run. And I am looking into better ways of doing this that won't take so long, but that's something that I'm still thinking through. In any case, that gives us our answer for part 2. Thank you for watching, and I'll see you next time.